Next, we discuss geometric distribution. In binomial distribution, we didn't care about a particular sequence of coin flips, right? Heads or tails. We were only concerned about the number of heads. But in geometric distribution, we do care about the sequence. Namely, if we flip a coin n times, actually not n times, if we flip a coin until we have a head. So let's say we flipped coin 4 times, all of them were tails, and at the 5th time, maybe we have a head. Okay, so this number of trials until we get the first head can be a random variable. Okay, sometimes it may be 10 times, sometimes it may be just 1, it may be just 100, and so on. So geometric distribution is a model for that experiment. Okay, so in this case, each of the flip is again a Bernoulli random variable. So probability Q, 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 and P. So in this particular sequence, we got the head at the 5th trial. And this probability is Q to the power of 4 times P, right? And the number of trial was 5. So in general, the random variable k that follows geometric distribution has this probability function, mass function, k q to the power of k minus 1 times p, where k can take values from 1, 2, 3, and so on. Okay, in this case we write k follows geometric distribution with parameter p. Okay, in this case we don't know how many times we will try flipping the coin, so that number is not specified. In fact, it is the random variable we are dealing with here. Okay, so again, try to calculate the geometric probability generating function for k. So the definition was this. Just use the definition. In this case, k starts from 1, okay? And it can continue up to infinity. And the probability mass function is this, so q k minus 1 p. Okay, if you calculate this, I will omit the detail. That is actually an exercise. You get this result. You should get this result. Hopefully this is right. 1 minus ps. Okay. So again, if you differentiate once and put s equal to 1, you should get, I will omit the calculation, and the result should be 1 over p. Okay, so this is the expected value for k. That means if the probability of obtaining a head is p, then the expected number of times you have to flip a coin until you get a head is 1 over p. And by using this generating function, you can also calculate the variance. So this is expectation of k, and variance should be 1 minus p over p squared. Okay, this is a little bit more complicated. expression. Okay, so that is the geometric distribution. Okay, now we study negative binomial distribution. This is actually an extension of the geometric distribution. In the case of geometric distribution, we were interested in the number of trials until the first head. Okay. In the case of negative binomial distribution, we are interested in the number of trials until we get r heads. Okay. So during the trial, we may get head once, twice, and 3 times. So in this case, r is 3. And what's the probability of this? 1, 2, 3, 4, 5, 6, 7 tails, and 1, 2, 3 heads. Okay, but we do not care about the order of heads and tails except for the last one. Okay, so these 2 heads could have appeared anywhere in this. So that means if this is the kth attempt, in this case 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in this case 10. So before the last one, there are k minus 1 attempts, trials, and out of which there were r minus 1 heads, right? So the combination of such arrangement is k minus 1 choose r minus 1. So that is k minus r. Okay. So, and this random variable is said to follow a negative binomial distribution. Okay. So to generalize this, we have such an we have parameter p and random variable k, which takes the values from r plus 1, r plus 2, and so on. Because we are interested in the number of trials until we get the rth heads. Okay, so the minimum trials should be r. Okay, so that means if we get all heads, only heads, r times, then we are done, right? So that's the minimum. And maximum can be infinity. Then the probability distribution function for this is given by k minus 1, choose r minus 1, and p to the power of r, like this, and q to the power of k minus r. So that means k minus r trials resulted in tails, and r trials resulted in heads. So this random variable is said to follow the negative binomial distribution. It's negative, it's not binomial. And we write k follows negative binomial distribution with parameters r and p. Okay, this r must be given and p must be given. Okay, why is it called negative binomial? To answer that, what is binomial? Why binomial distribution is called binomial distribution? So binomial distribution, this name comes from the binomial theorem. So if you have x plus y all to the power of n, then if you expand this, you have this kind of sequence. Okay, 0 to n, and n choose k, x to the power of k, y to the power of n minus k, right? So these coefficients can be calculated from Pascal's triangle. Okay, so when n is 1, it's x, y. So it's x, just x plus y. So that is 1 choose 1, x, and 1 choose 0, y. That's it. And when x plus y squared, it's x squared plus 2xy plus y squared. And this is to choose 2. And this is to choose 1. And this is to choose 0. Okay, so how do I get this Pascal's triangle? So suppose there is, so this corresponds to x and y, right? So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 0 is 1, and again put 0 here, and 0 plus 1 is 1, 3, 3, 1, and so on. So these coefficients are the binomial coefficients. Okay, so if you make it cubed, you will have these coefficients. So this appears in binomial distribution. If you look at the binomial distribution, this is exactly the form of the probability distribution. Okay, if you put x equal to p and y equal to q, and that is exactly binomial distribution. So in the case of negative binomial distribution, what's the difference? Okay, to consider this, try to expand this function. Okay, so if you expand this into Taylor series around x equal to 0, you should have this, and minus 1, minus 1. So this is Taylor series. Around x equal to 0. Okay. And if you change variables here, let's say, how do I change this? So instead of starting from n equal to 0, we start from k equal to r. Okay, so that is, we change variables here. We set this equal to k. Okay, in that case, when n is 0, k is r, right? So let's say k is equal to n plus r. So when n is 0, k is r. K minus 1, r minus 1. And this n should become k, sorry, not here. this n should become k minus r. Okay, when k is r, this is 0. So that corresponds to n equal to 0. Yes. So if you compare this with the probability distribution function for the binomial distribution, that is k minus 1, r minus 1, pr, q, k minus r. See, this is the coefficient of negative binomial distribution. Okay, negative, okay, just in case you don't get it, negative appears here because this thing is 1 minus x to the power of negative r, right? So this is, so to speak, a negative binomial theorem. Okay. So now, suppose we have k1, k2, and up to kr that follows geometric distribution with parameter p. Okay, they are independent and identically distributed random variables. Okay, then we define a new random variable as the sum of these geometric random variables. Okay, then actually this new random variable follows the negative binomial distribution with parameters r and p. Okay. You should now know how to prove this, at least in principle. Okay. So we have seen the probability generating function for geometric distribution, right? So from this definition, we can calculate the probability generating function for this random variable x. So that will be just the geometric generating function for k to the power of r, because these k1, k2, kr, they are independent and identically distributed and follows geometric distribution. So this gk of s is the probability generating function of the geometric distribution. Okay. Then calculate the probability generating function for this distribution, so negative binomial distribution. Okay, if you use this negative binomial theorem, it should be easier. Okay, because let's see. Let's try to calculate that one. So we have probability function of negative binomial distribution as k minus 1, r minus 1, pr, q, k minus r, and k is r plus 1, and so on. Okay, so the definition, I think this case I should write, never mind. This case, the probability generating function is k. K doesn't start from 0, it starts from r. Okay, just be careful. And s to the power of k and k minus 1, r minus 1, pr, q, k, r. Now, this factor, p to the power of r, it's a constant. There's no k here, so we can put this out. Okay, so let's put this out of the summation. And let's see. And this s, we can, if you compare the powers of this s and this q, they are a little bit different, but they can be made the same by subtracting r here and multiplying r here. But this is constant, so we can again put this outside. So let's see, pr, sr. So maybe we should put them together. So ps to the power of r and summation k minus 1, r minus 1, and this and this. So s q to the power of k minus r. Okay? Now, look at this part and compare it with the negative binomial theorem. So this one. Let's see. Can we move this? So this SQ corresponds to this X. So we should have, let's see, we should have this ps to the power of r, and applying the negative binomial theorem, it should be 1 minus qs to the power of negative r. Okay, so just put this to the denominator. We have ps and qs, everything to the power of r. Okay, now this is, what's this? Remember the probability generating function for the geometric distribution? That was this, ps minus qs. So this generating function for the negative binomial distribution is the power of the generating function for the geometric distribution to the power of r. So that means the probability generating function of this random variable is the same as the probability generating function for the negative binomial distribution. So that means those distributions are equivalent. They are the same. Okay. So we see similar patterns over and over. Okay. And by using this, you should be able to calculate the expectation value of this random variable, negative binomial random variable, and variance. Okay, which are, I don't calculate here, but you should try. So the variance should be r 1 minus p over p squared. And again, this is just r times the expectation value of geometric random variable, right? And this also r times. So this is okay. Actually, this is easy to understand. So this k is a sum of geometric random variables, right? R. So you just split the summation, and each of them is just 1 over p. So it's r over p. And for the variance also, okay, since these geometric random variables are independent, we don't have any covariance components. So the variance of independent random variable, sum of independent variables are. So since they are independent, we can split the variance. If they're not independent, we cannot do this. R. So that is 1 minus p squared. So same thing. Just r p squared. Okay. So that is the negative binomial distribution.